All right, so today we're going to try to cram an ocean into a teacup.
Oh, wow.
Not literally, of course,
Yeah.
but that's kind of what simulating the quantum world on a classical computer is like.
At least according to a certain Richard Feynman.
Exactly.
Yeah, his 1982 paper, Simulating Physics with Computers,
That's the one.
really laid out this whole idea
Yeah.
that the universe is, it operates on quantum principles.
Mm-hmm.
And to really simulate it, you need a computer that can speak the same language.
So it's like we've been trying to translate Shakespeare into emojis.
Yeah.
Like you just lose all the nuance.
Oh, I like that analogy, yeah.
Classical computers are great for tasks with clear yes or no answers.
Right.
But the quantum world,
Yeah.
it's all about probabilities and entanglement.
It gets fuzzy.
Things get fuzzy.
Yeah.
And Feynman saw this as like a fundamental roadblock,
Absolutely.
not just a temporary tech limitation.
Not at all.
This is like baked into the nature of reality.
Exactly. He argued that classical computers, because they rely on these local connections, they would really struggle to efficiently simulate quantum systems.
So to illustrate this, he pointed to a very specific type of experiment.
Right.
The two-photon correlation experiment.
Yes.
All right, break that down for me. Two photons. Correlation? I'm intrigued.
Okay, so picture this.
Okay.
You have a source that emits two entangled photons,
Okay.
and they travel in opposite directions towards detectors.
Mm-hmm.
But before each detector, there's this thing called an analyzer
Okay.
that filters the photons based on their polarization.
So entangled, this means their fates are linked even across large distances, right?
Yes.
Like a quantum version of you jump, I jump.
Precisely, and here's where it gets really interesting.
Okay.
Quantum mechanics predicts that those detectors will agree on whether or not they detected a photon 75% of the time.
Okay.
Even if those analyzers are set at different angles.
Hold on. That means they're somehow influencing each other instantly across space.
It seems that way, right?
That seems to break the rules of physics as we know them.
Yeah, and that's exactly what makes this experiment so challenging for classical physics to explain.
Yeah.
Because even with these things called hidden variables, classical physics can only predict agreement around 67% of the time.
Okay.
So there's this discrepancy, and this discrepancy is actually a key consequence of something called Bell's theorem,
Okay.
which essentially shows that the quantum world is operating by a totally different rule book.
So to simulate this experiment accurately,
Yeah.
you can't just tweak a classical computer.
Right.
You need a system that inherently understands entanglement.
Exactly. You need a system that speaks the language of quantum mechanics.
And that was Feynman's radical proposition.
Yeah,
To build computers out of quantum elements themselves.
that's right.
He envisioned a machine that could harness these bizarre quantum phenomena to unlock this whole new level of computational power.
A whole new way of computing.
So he wasn't just pointing out a problem, he was suggesting a solution.
He was.
A quantum computer.
Yes.
And what a leap that was.
It was a huge conceptual leap, and it's really amazing to think about.
Yeah.
Because his 1982 paper really planted the seeds for this whole field of quantum computing that we know today.
Now fast forward to today.
Yeah.
I mean, this field has just exploded.
It has.
There are so many different technologies vying for dominance.
Right.
But building these machines is hard.
It's incredibly difficult.
What are some of the big challenges?
Oh, well, one of the major challenges is just controlling these individual qubits, right?
Okay, so qubits, these are the quantum bits of information.
Yes, exactly.
Okay.
And then there's the issue of scalability. Building systems with lots of qubits and keeping them stable.
And of course, there's decoherence.
Yes, the dreaded decoherence.
So decoherence, this is when the quantum system starts acting more classical because it's interacting with its environment.
Right, it's like the quantumness is leaking out of the system.
Like the quantum equivalent of spilling your coffee and ruining your nose.
Uh-huh. I love that analogy.
It just kind of makes it all messy and unusable.
Yeah, exactly. It makes the system less powerful.
And this is something Feynman anticipated,
Yeah,
right?
he did.
He knew that building these machines
Yeah.
was going to be an enormous engineering challenge.
Absolutely. It's like trying to build a house of cards in a hurricane.
So just constructing these things was a major hurdle, let alone using them for complex simulations.
Right.
So let's talk about the different types of quantum simulations that are being explored these days.
Okay, so there are three main approaches.
Lay them on me.
All right, so first we have digital quantum simulation.
Okay.
And this is where you use a universal quantum computer to simulate another quantum system by breaking down its evolution into a series of quantum gates.
So it's like you're programming a quantum computer to mimic the system you're interested in.
Exactly.
Oh, cool.
And then we have analog quantum simulation,
Yeah.
which I think is probably the closest to what Feynman actually had in mind.
Yeah, I was going to say that sounds a lot like what we were just talking about, where you're trying to map the system you want to study onto a controllable quantum system.
Yes, you're basically finding a physical system that behaves in a very similar way to the system you want to study, and you're using it as a direct stand-in.
So you're not really simulating it, you're kind of building a mini version of it.
In a way, yeah.
Okay, that's cool.
And then lastly, we have quantum information-inspired simulation.
Quantum information-inspired simulation.
This one's a little bit different.
Yeah, what is that?
So this approach uses techniques from quantum information theory to actually improve classical simulation algorithms.
Interesting.
It's like we're trying to squeeze more power out of our current computers by thinking about problems in a quantum way.
So even classical simulation techniques are getting a boost from quantum thinking.
Exactly.
Okay, I like that.
Yeah, it's pretty neat.
So what are the real advantages, though, of using actual quantum simulations?
Right. Well, one area where they really shine is in tackling this thing called the sign problem.
The sign?
Yeah, it's a challenge that pops up when you're trying to simulate these things called fermionic systems.
Fermionic systems?
Like electrons on classical computers.
Okay.
But quantum simulations can potentially bypass this issue entirely.
So it's not just about speed.
Right.
It's about solving problems that are fundamentally difficult
Exactly.
for classical computers to handle.
Yeah.
Okay.
And there's more.
Okay, tell me more.
Quantum simulations are really good at handling the inherent complexity of quantum systems, much better than classical ones, especially when you're dealing with these highly entangled states.
Okay.
So this opens up a whole world of possibilities.
Imagine being able to simulate complex molecules for drug discovery.
Yes.
Or delve into high-energy physics phenomena that we can't recreate in a lab.
Right.
Or what about the early universe?
Yeah, those are exactly the kinds of problems that quantum simulations could really revolutionize.
So we're talking problems that would take classical computers years, centuries, maybe even longer to solve.
Exactly. Potentially even impossible for classical computers.
Okay, I am officially on board the quantum simulation hype train. But I have heard that we're currently in this NISQ era.
Yes, the NISQ era.
What does that mean for all these amazing possibilities?
All right, so NISQ stands for Noisy Intermediate Scale Quantum.
Okay.
It essentially means that we have these quantum computers with, dozens to hundreds of qubits.
Okay.
But they're still prone to errors, and they lack something called fault tolerance.
So it's like we have these incredible tools, but they're still a bit finicky.
They're a little bit finicky, yeah.
Does that limit what we can do?
It definitely presents challenges, but even with these limitations, NISQ devices are being used for some really incredible experiments and research.
Okay.
It's a crucial stepping stone towards more powerful and more reliable quantum computers in the future.
So where are these NISQ quantum simulations making a real impact?
Well, one area where they're really making waves is in condensed matter physics. They're helping us to understand these exotic materials, like superconductors and topological insulators, which have the potential to revolutionize electronics as we know it.
And I've also heard whispers about applications in high-energy physics.
Yes.
Are those living up to the hype?
Absolutely. They're being used to simulate the interactions of fundamental particles, like quarks and gluons, which could unlock secrets about the universe that are currently beyond our grasp.
Okay, I need to hear more about that, but first we need to take a break.
Sounds good.
We'll be right back with part 2 of this deep dive into the world of quantum simulations.
All right.
Where we'll explore even more of the fascinating applications and possibilities of this revolutionary field. Stay tuned.
I'm excited. It's really remarkable how Feynman's vision has really rippled outward, influencing fields far beyond just physics.
Yeah, that's what's so exciting about these deep dives, seeing how these seemingly abstract concepts actually connect to the real world in these unexpected ways. What other areas are getting in on this quantum action?
Well, one field that's really ripe for disruption is material science.
Okay, material science.
Because after all, materials are all about how atoms and molecules interact, which is quantum mechanics at its core.
It's like we've been trying to design houses without understanding the properties of bricks.
Exactly.
Quantum simulations could change all that.
Yeah, with quantum simulations, we could actually design materials with entirely new properties.
Oh.
Things like super efficient solar cells.
Wow.
Room temperature superconductors.
Okay.
Or even self-healing materials.
Self-healing materials.
Yeah.
Now, that's straight out of a sci-fi movie.
I know, right?
I'm picturing like a phone screen that repairs its own cracks.
Yeah.
What about drug discovery?
Oh, yeah.
I've heard rumblings about quantum simulations revolutionizing that field, too.
That's another area with just immense potential. Because right now, designing new drugs, it's a really long and expensive process with a lot of trial and error.
Yeah.
But imagine being able to simulate how a potential drug molecule interacts with the human body at the quantum level.
That would be game-changing.
You could pinpoint the most effective drugs with far fewer side effects, and you could speed up the whole process.
Okay, I'm completely with you on the potential here.
Yeah.
But with all this hype, is there a danger of overpromising? I mean, are we getting ahead of ourselves?
It's a valid concern.
Yeah.
We're still in the early stages, and building fault-tolerant, large-scale quantum computers is a monumental task.
Right, so no quantum laptops anytime soon.
Probably not. Haha.
Okay, good to know.
But I think we'll see a more hybrid approach.
Okay.
Where quantum computers are accessed remotely.
Okay.
Kind of like cloud computing.
So instead of owning a quantum computer, you'd essentially rent its power for specific tasks.
Exactly.
That actually makes a lot of sense.
It does, because not everyone needs a quantum computer for their everyday work.
Right.
It's more about having access to this incredible resource when you need it for those really tough computational problems.
And I imagine this cloud-based model will really drive innovation.
Yeah, it'll allow more people to experiment with quantum simulations and develop new applications without having to build their own quantum computers.
So it's about democratizing access to this powerful tool.
Exactly.
And as the technology matures and costs come down, we might even see specialized quantum devices designed for specific industries like pharmaceuticals or materials, science.
Potentially, yeah.
Okay, that's a future I can definitely get behind.
Yeah.
But let's zoom out for a moment.
Okay.
Thinking back to Feynman's original vision, what would you say are the biggest open questions that quantum simulations might help us answer?
Oh, wow. That's a big question.
The really big mind-bending stuff.
Well, one of the most profound questions, I think, is about the nature of consciousness.
Consciousness.
Could quantum effects play a role in how our brains process information and create this thing called subjective experience?
Are we talking about quantum consciousness here?
Yeah.
That's a whole other rabbit hole we could explore.
It is. It's a very controversial topic.
Yeah.
But some researchers believe that quantum simulations could provide new tools to explore these questions.
It's fascinating to think about.
It is.
What other big mysteries are out there? Just waiting for quantum simulations to shed some light on them.
Well, how about the origin of life?
The origin of life?
Could quantum simulations help us understand how those first self-replicating molecules emerged from the primordial soup?
So, like, simulating the very beginnings of life on Earth.
Yeah.
That's amazing.
It is. And it really gets back to Feynman's core idea that to truly understand the universe, we need to be able to simulate it at its most fundamental level.
Okay, so we've got consciousness, the origin of life. What else is on the quantum simulation bucket list?
Well, how about the nature of dark matter and dark energy?
Dark matter and dark energy.
These mysterious entities that make up the vast majority of the universe.
Yeah, we still know very little about them.
Very little.
And you're suggesting that quantum simulations could help us unlock those secrets.
It's a possibility.
Wow.
By simulating the behavior of particles at extremely high energies.
Okay.
We might gain insights into the nature of dark matter and dark energy, things that are currently beyond the reach of our experiments.
This is what I love about this field.
Yeah.
It's about pushing the boundaries of what we know.
Absolutely.
Exploring the most fundamental questions about the universe.
Yeah.
It's incredibly inspiring.
It really is. Quantum simulations offer this glimpse into the deepest mysteries of nature, and they have the potential to revolutionize countless fields.
Yeah.
From medicine to material science to cosmology. It's an incredibly exciting time to be involved in this research.
So for our listeners who are now completely hooked on quantum simulations, what's the key takeaway? What should they be thinking about after this deep dive?
I think the most important thing to remember is that the future of quantum simulations is still being written, It's a field full of possibilities and challenges and profound questions.
Yeah.
But it's also a field driven by curiosity.
Yeah.
A desire to understand the nature of reality at its deepest level.
And it's a field that welcomes everyone.
Yes.
Whether you're a scientist, an engineer, or just someone with a curious mind who wants to explore the frontiers of knowledge.
Absolutely.
So if you're fascinated by the idea of using quantum mechanics to unlock the secrets of the universe, then this is the field for you.
It is.
Well said. And on that note, I think it's a perfect time to wrap up our deep dive into the world of quantum simulations.
Okay.
Thanks for joining us on this incredible journey.
Yeah.
And a huge thank you to our expert for sharing your knowledge and insights with us today.
It was my pleasure.
And to all our listeners out there.
Yeah.
Keep exploring, keep questioning, and keep that quantum curiosity alive. This is The Deep Dive signing off.
Bye.